In the last lecture, we discussed the Dirac field. We solved the Dirac field in the classical case. So we have now a solution to classical Dirac equation in terms of plane waves. And we're going to use this plane wave basis as the building block to guess a quantum theory that corresponds to the Dirac field. So today's objective is to build the quantum Dirac field, not the classical Dirac field. Now, to remind you of the story of quantization, we have the space of quantum theories, some kind of abstract category. Objects are Hilbert spaces, morphisms are unitaries, something like that. And then we know that the emergence of the classical world is through the process of decoherence and also the restriction to low energies and large scales. And in this limit, this classical limit, the world is still very much quantum. It's no less quantum in this classical limit of the large amounts of decoherence, low energies, and large scales. It still is exactly as quantum as it was before, but it's effectively well modeled by a classical theory. So that's the lesson of quantization. Quantization is the process whereby we take some effective classical model that's worked very well for centuries, and we try and guess the quantum theory that led to it after the process of decoherence set in, after we focus on low energies and large scales. So we've arguably successfully carried out this quantization procedure, this inverse problem of guessing a quantum theory. We've arguably carried that out for the Klein-Gordon field. Process, as I've emphasized before in previous lectures, quantization is the art of the educated guess. We want to guess that quantum theory with a given specific effective classical theory. And I reckon we've got good reasons to think that we were successful in the case of the Klein-Gordon field. Maybe you are not completely comfortable with the interacting phi-4 field. But as you gain more experience in these kind of things, I would argue that you would also eventually agree that's a reasonable quantization as well. Today, we want to carry out this game for the Dirac field. So we know that the classical theory that we're interested in, we've already worked out its classical dynamics. It's Hamilton, it's Lagrange density. The Lagrange density in question is this one here. I'll explain the slash notation soon. So we know, oops, I was on the wrong side. In the previous lectures, we've been analyzing a purely classical theory of spinors, the Dirac spinor, whose Lagrange density is this. And today we want to start guessing quantum theories. So we want to go backwards and find some quantum theories with this particular classical limit. That's what we'll do today. And we've had some experience now in doing this, so we know that we can guess these theories in terms of free quantum theories. It means their Hamiltonians are quadratic. And our strategy will be the same as it was for the Klein-Gordon field. We're going to guess our quantum field by basically sticking a harmonic oscillator on every degree of freedom labeled by a solution of the Dirac equation. That's the strategy for today. Same as it was for the Klein-Gordon equation. And let's commence our story with a cautionary tale. We're not going to quantize the Dirac field correctly the first time round. We have actually two options to carry out this quadratic quantum theory quantization argument. We could attach a bosonic degree of freedom to every classical solution of the wave equation, or a fermionic degree of freedom. We know that from last semester in the advanced quantum theory, there's two possible ways to build Hilbert spaces of identical particles in quantum mechanics. One is via bosons and one's via fermions. Now, in the previous time when we discussed the Klein-Gordon equation, we attached a boson degree of freedom to each plane wave. Morally speaking, that's what we did. And that worked out fine. We could have attached a fermion degree of freedom to each plane wave degree of freedom of the Klein-Gordon equation. That would have also been a strategy. We didn't pursue that strategy. That would be, roughly speaking, a scalar fermion field theory. This sort of thing does appear, but in the next semester. And it certainly doesn't model degrees of freedom that we can experience at the quantum electrodynamics level. But we could have done that, right? We could have attached a fermion to every degree of freedom. We could attach some vector of fermions and bosons, and indeed you can do that. But we're not going to do that. Instead, we're just looking at the simplest possible field theories that you can build in this course. And we're going to try and do that with the Dirac field. We're going to start by doing bosonic second quantization. And I think there's an interesting lesson to be learned here in doing this, because it tells us what we consider a valid quantization. Because what we're going to do will, in some sense, actually work, but we will not quantize the Dirac field with a bosonic approach, because this quantum theory that we will produce will be sick in a very particular way. So I'll explain that in the next couple of moments. So let's suppose that the quantum theory we're trying to build is a theory of many bosons. So to cut somewhat of a long story short, you might guess that we should impose equal time commutation relations on the field operators. So it's a reasonable guess for how to quantize a Dirac field. And this A labels the spin index like that. So a Dirac field is like 4 fields labeled by the spin index. This worked very well when we did it for the Klein-Gordon equation. So we could be optimistic it works well for the Dirac equation. And we could expand our field operators, our potentially reasonable quantum field operators, in terms of this plane wave basis to define some annihilation and creation operators for momentum modes. So it's a perfectly legal thing that we're welcome to try. We can define annihilation and creation operators A and B according to this recipe. And consistency with these canonical commutation relations forces these annihilation operators here to obey also a canonical commutations algebra. So because this is the wrong way to do it, I'm not going to spend so much time deriving these equations. You're welcome to go through some of these derivations in more detail, or you're just welcome to believe that these derivations are correct because it's the wrong way anyway. And then all the other canonical commutation relations are 0. So far we've been paralleling the discussion of the Klein-Gordon field, and so far there's no contradiction. This is just defining some operators. Now the quantum Hamiltonian well, we get that by putting the hat on the classical Hamiltonian. That worked very well for us with the Klein-Gordon field, just putting the hat on the Hamiltonian. And, you know, some derivations which is an exercise if you want to do it. We're going to end up being able to express our quantum Hamiltonian H in terms of these P's and B's and Q's. And we get a slightly unhappy answer. Namely this. So up to now, everything's fine. But this is bad. So if we decide to bosonically quantize this Dirac field, then naively putting a hat on the Hamiltonian will lead us to writing down this particular, plus an infinite constant. We can't get rid of that. But of course, infinite shifts of energy are not observable, so at least we're happy with that. But we'll end up writing down this Hamiltonian here. And this is bad news. And the reason is this Hamiltonian has no ground state. So there's real physics that's wrong here. It's possible to create states with arbitrarily low energy by simply occupying these modes here with B operators. Every time you increase the B number, the number of B particles, the energy drops by a factor of omega p. There's nothing stopping you from continuing to occupy those modes to make the energy lower and lower and lower and lower. So what this Hamiltonian is like is it's like modeling an inverted pendulum. So it's as you occupy more and more modes, the system gains more and more energy and is unstable. And it runs away. There's a runaway solution that just creates infinitely many bosons in all these B modes in order to get lower and lower energy. So it's extremely unstable as a physical model. And so physically that's bad, right? We don't see this happening, that one moment we're nice and stable, the next everything dissolves into a thermal nightmare of bosons being created out of nowhere. This just doesn't happen. So there must be something wrong. So there's several things that could be wrong. So let's go through the simplest through to the most interesting. So the simplest thing that could be wrong is that these derivations are wrong, that we made a mistake. Okay? That could have been wrong. But, well, people have checked this. You can check it. Pretty sure it's correct. The second, and this is slightly more interesting, is that our naive quantization of adding the hat on the Hamiltonian was wrong. It might be that there's another quantum Hamiltonian out there that's not found by naively putting the hat on, that has the right classical limit. Now to that, I don't know how to argue against that actually, because you somehow have to argue against the infinity of all possible Hamiltonians that there isn't one out there that wouldn't actually do the right job. So I think it's probably logically open still that there is a bosonic quantization of the Dirac field, simply by a different Hamiltonian H. It's logically possible, but it's probably extremely baroque if it exists at all. And furthermore, remember what we want is not just a Hamiltonian, but we want a full representation of the Poincare group, unitary representation. You know, in terms of a local field theory, I think the odds are against that being possible, but even if it was possible, these bosonic quantizations would probably be so horrendously ugly that there's no point in pursuing them, because we have a third option, the most elegant of all, is to simply change the way we guessed our Hamiltonian and guess that it's a quantum theory of fermions rather than bosons, and that works out rather well and matches the experiments. So I think we should just, we can stop talking about looking for a bosonic quantization because we found one that actually works and matches physics. And that, after all, is what we do in physics. So the correct quantization of the Dirac field is via the Fermi second quantization. We postulate the existence of a collection of quantum fields that obey not the bosonic commutation relations, but the fermionic anti-commutation relations. Otherwise, things remain just as before. Remember, psi dagger is the conjugate momenta, right? That's why it's there for the Dirac field. So we're going to impose these instead, and things will turn out to be just fine. So bosons are no more fundamental than fermions. They're just a different way to obtain a theory of identical particles in quantum mechanics. So these should be valid. There's no reason to prefer a bosonic over a fermionic quantization, except that we somehow think that things are bosonic from our classical everyday experience. Okay. So we're going to impose these anti-commutation relations and repeat the whole sequence of derivations that goes from expressing the field operator in terms of the position to expressing the field operator in terms of momentum, defining creation and annihilation operators, and then a Hamiltonian. So that's the task for today, to go all through these steps. Actually, I will skip a good number of these steps because they're very similar to the Klein-Gordon case. All right, the first step, of course, is to define annihilation and creation operators so that we can build ourselves a Fock space. Okay, so we're going to expand the field operators in terms of these momentum eigenbases coming from the solution of the Dirac equation. there's a minus. No. All right. So we can expand the field operator to define A's and B's this way. And similarly, we can expand psi bar in terms of the A's and B's. And remember, the bar operation is take dagger and multiply by gamma naught. And a little while later, you end up with these expressions. Well, actually, that's not an exercise. That's, well, this is, yeah. The first one's a definition. The next step is to put the hat on the Hamiltonian, express the Hamiltonian in terms of these A's and B's. And then we'll see something pretty remarkable. I guess I'll call these star star. So according to this definition of the A's and B's, the consistency with star star is going to enforce some anti-commutation relations on our A's and B's. So here they come. So if you work through, if you substitute this expression into this anti-commutation relation up here, and you ask what do the anti-commutation relations between A and B have to be, A and B dagger, A and A dagger, and so on, then you will quickly conclude that they should obey these particular anti-commutation relations. And all other brackets are 0. Now, So this procedure of putting hats on the classical Hamiltonian, when you express that operator in terms of A's and B's, you find something rather interesting. Up to an infinite shift in the zero of energy, we write down this thing. This is the first naivest way of quantizing the Hamiltonian, and we end up writing this down. And that minus sign has disappeared, the minus sign that appeared in the bad Hamiltonian. It's no longer there, right? It's exactly the same, apart from this minus sign. And that minus sign disappeared because the anti-commutation relations give you a minus when you move things past each other, whereas the commutation relations give you a plus. And there it goes. Poof, it's just fixed. This is now a positive operator with a unique ground state with no particles, unique vacuum state. Ground state is omega. Fantastic. That is really an elegant solution to the problem of the bosonic quantization. So once you see that, I think you should find that pretty compelling as an argument for why this is the right quantization of the Dirac field. Yes. So this is our quantum theory that we're going to start calling the quantum Dirac field. We don't yet have the right to call it a relativistic quantum field theory. All we've done is we found a Hilbert space and an operator generating time translations. But to call this a relativistic quantum field theory, we're going to need a full representation of the Poincare group on the Hilbert space of this theory. And only then do we have the right to call this a relativistic quantum theory. So we're like 1/10 of the way there, right? So we've got one generator out of 10 to check. We've checked. We haven't done the rotations yet, so we don't even know if it's a rotation invariant theory. We haven't done the translations in space. We haven't checked that they obey the right commutation relations. And we certainly haven't done the boosts. So that's the business to which we will now turn. We're going to start looking, we're going to write down generators for all the Poincare transformations. Actually, we're going to sort of take shortcuts here and there so that we don't spend too long proving that it's a relativistic quantum field theory. Yeah, I think I end up only implicitly defining the representation. But the same arguments that we use for the Klein-Gardner field directly apply here. You use the Noether theorem to guess the charges that generate each of these transformations. So one of the most important groups that we ought to study is just the translation group. And the generators of translations are momentum operators. And we're just going to put hats on the classical momentum generators. That's our general strategy for guessing operators. And, well, turns out to work, of course. So this here is the momentum density for the Dirac field, which you get from Noether's theorem. This is the charge, and putting the hats on gives us the quantum generator of translations. So we skipped some steps getting to this first definition. Now we're going to expand our field operators, which are expressed here in position, in terms of the A's and B's, which we get from the solution to the Dirac equation, the momentum basis. And we come up with a rather nice looking formula. Yeah. This pretty much parallels the answer for the Klein-Gardner equation. And this is a vector of operators here, this line here. This really means we have a Px, a Py, and a Pz. Similarly, this is a vector in here. Like that. So we've got a vector of 3 momentum operators defined according to this prescription of hats, which when you substitute in the field operator in terms of these creation and annihilation operators is given by this expression here. And you can check the commutation relations. This is important. Commutation relations. These fundamental fields obey anti-commutation relations, but they're operators on a Hilbert space. And if we're to get a representation of the Poincare group, we know that Poisson brackets have to be replaced with commutators. That's why we need to check the commutator of P and H is 0. So don't be distracted by the fact that these field operators themselves obey an anti-commutation relations. Don't be distracted by that. The things that you need to check actually obey commutation relations. And you can work them out in terms of anti-commutation relations. So it's not. This is a very possible calculation, and you can do that as a simple exercise. Yo.
In this commutator, this P is Px plus Py plus Pz.
Oh yeah.
Okay.
Px or Py or Pz.
Okay.
if you like, I could do this, right? J maybe that looks a little less crazy. It's equivalent. It's whether or not you prefer these notations. It's a bit premature to make this statement, but it is true because everything will work out. These operators here create particles, right? That comes immediately from this representation here. Right, you can check that. That's a nice little exercise in anti-commutation relations. Similarly, if you apply the P operator on this single particle momentum eigenstate, vacuum, then you get Pj. So insofar as we're happy to say that P measures momentum, H measures energy, then the single particle eigenstates that you get by applying A's and B's to the vacuum will have the right energy momentum 4 vector. It's a good sign. But it is not yet a relativistic quantum field theory. Okay, I'm going to give you the real shortcut to getting the representation theory of the Lorentz group here in the Dirac field. We didn't do this for the Klein-Gordon field. This is another approach to getting unitary representations. We're going to first define some normalized, in quote marks, because they're not normalizable, so you have to take this with a grain of salt, that word. Normalized single particle states, and they're defined by just as analogously for the Klein-Gordon equation, we multiply by this square root of 2 omega p so that things are, the completeness relation will work out later on. So it's just a scalar multiple of your naive single particle state. And the reason we say it's normalized is that when you compute the scalar product, unit product between two of these states, then you get something kind of nice. And we previously argued that this is an invariant density, right? 2 omega p delta 3 p minus q. So I've got star before, so we'll make this I. This is sort of less systematic than the way I advocated for the scalar field. I mean, there's one way to get a unitary representation of the Poincare group if we followed the strategy we had for the scalar field, right? We could first work out the quantum form of all the generators of the Lie algebra of the Lorentz group, and then check that the commutation relations all work out, and then we'll be happy that we have a unitary representation of the Poincare group. That's what we did for the scalar field. Another way is to just sort of define it and check that it works, because we could do that other strategy, which is systematic. What I advocated is that there's, in the previous case, there's like an algorithm for each step of that process. Getting the generators comes from Noether's theorem. Getting the quantization comes from putting hats on. So you don't have to be particularly clever, you just have to just carry out this algorithm to get the unitary representation. Here we're going to be a little bit more clever and just simply define it, and define it correctly. It's always a valid strategy is to look at the answer and then write down the answer. So this is what we're doing here. I didn't want to show you this the first time round, because then you'd be like, well, how did you know to do that? Slightly awkward notation here. I don't have a good way to write this. I guess line under that. See, these operators here are indexed by a 3 vector. Lorentz transformations act on 4 vectors. So what do I mean here? So I have to So drawing a line under it means just taking the three spatial components of this 4 vector. So you can do that definition. You can just write that down on a piece of paper as though from divine insight, and then check that it works. And also we do the same for the B's. So once we have that, we've actually got the unitary full representation of the Poincare group. If we define it like that, then we're done. Because Fock space is generated by products of these operators on the vacuum, and then you just extend the action of this through the whole of Fock space. So that's super quick. Well, let's exploit this knowledge straight away to calculate the action of the Lorentz transformations, the Poincare transformations, on the spinor field itself. Now that we have this, take the dagger and we have it for the daggers, we can insert this whole definition into the spinor field, so we can see what the Lorentz transformations do on the spinor field. This is a really nice calculation, actually. I suppose I'll do all of it because it's nice. So the first step is to substitute in the expansion for psi hat that we already have per definition. I guess I'll do this on the next line, otherwise it won't fit. Yeah, I guess it doesn't fit. Okay, that's step one. Just insert the definition of the A's and B's inside the field operator. And now we're, like, in some sense, we're almost done, right? Because all we have to do is bring this unitary here, make it apply to the A, make this one apply to the B, use our definitions, change a variable, we're done. So let's do those steps a bit slower than just saying them, because it is quite nice. As you get involved in more physics research and you get used to nothing actually working whenever you try out a calculation, there's something very satisfying about doing a calculation where you know the answer is correct. Beware, I just fixed up a dagger missing in the line above. Oops. And I forgot the VS. There we go. Now it's better. And then we're going to do a change of variable, right? That was inevitable. We have things with respect to lambda p here. We have things with respect to p in the integral. The change of variable is imminent. Let's do that. We let p twiddle be lambda p and carry out the change of basis. We use the fact that this is an invariant measure, right? Remember how we proved long ago that's an invariant measure, so under the change of variables it doesn't change. Okay, let's check everything actually went according to plan. So let's start here. P equals lambda inverse P twiddle. Yep. So there's an inverse missing here. Inverse missing there. Otherwise, everything is fine. And that's an omega p twiddle, an omega p that cancels with that to give the omega p twiddle there. Okay, so all is good. And the last step is the best. This is lambda half times by the spinor field evaluated at lambda minus 1 of x. Yo.
Why do you write the capital delta minus 1 after the p?
Why do I write the capital delta minus 1 after the p? Capital lambda minus 1 after the p. So this is p dot x is just the inner product of p with x. So it's symmetric. So, I mean, it's slightly stupid notation, I admit, but that's... I want to emphasize that we can transfer the Lorentz transformation from the p onto the x. It's crucial that it's on the x. Okay, either you'll just immediately see what I'm about to write down, or you'll need to do like one line to check. Actually, in my notes, I took 3 or 4 lines to check the next statement, but it's not. So this is a great result, right? Because we've taken this admittedly ad hoc definition in terms of annihilation and creation operators. We've applied it to the field operator, and we found that the field operator as a quantum operator transforms like this. So this is good evidence that this unitary we've defined is indeed like a representation of the Lorentz group. Of course, to really convince ourselves of the fact that this is a representation of the Lorentz group, we're going to have to check at some point that all the commutation relations for the Lie algebra are obeyed. There's no particular way to escape that, but at least doing it this way saves some sort of deductive steps. If I write out the answer, then it always helps, right? So to convince ourselves that this satisfies the full Lie algebra, the Poincare group, the generators of this definition, requires some more calculations. I don't think I've actually done the boost generator in this course. So in the end, that might be a calculation we just leave as a assignment sheet question. It's a good one. But what I have done is the angular momentum. Which is the generator of rotations. It's the conserved charge corresponding to rotation invariance under Noether's theorem. We're talking classical for a moment. So if we take a classical spinor field and subject it to a rotation, then we know what comes out already, because a rotation is a Lorentz transformation. so that's not so hard. So infinitesimal rotations are what you get when you don't rotate by a lot, but only a little. And we've already done this in the sense that we have the general expression. There was a mistake 2 lectures ago. I just want to take this opportunity to correct that mistake. 2 lectures ago we discussed infinitesimal rotations and infinitesimal boosts, and I wrote down a formula for the infinitesimal rotations, and I had a minus sign there. That was incorrect. There is no minus sign for the rotations, there's only a minus for the boosts. And we want the quantum version of S of this sigma 3 here. So we're going to have to put hats on. Okay, under an infinitesimal rotation, a spinor transforms as follows, right? So if we define delta psi x as the transformed version of psi as observed at point x minus the untransformed version of psi as observed at the same location x, then we got a formula for this, thanks to this infinitesimal expression here. And that's the formula right there. So the transformed version of the field evaluated at point x, well, we're doing a rotation in the xy plane, so we add a bit to the x depending on what y was, we add a bit to the, we subtract a bit from y depending on what the, should be an x, shouldn't it? Yep. Depending on what the x was, and we leave the z component alone. We're doing a rotation around the z-axis here. And this comes from the lambda to the lambda half. This is the lambda half part of the transformation, and this is just the lambda minus part of the transformation there. Now this is infinitesimal, so we're allowed to use Taylor's theorem to express this as a linear combination of psi evaluated at x minus some first order correction stuff. theta is meant to be very small. And that defines for us delta psi x as we need it for Noether's theorem. So we're going to apply Noether's theorem next. Okay, so remember Noether's theorem way back when in lectures 1 and 2. We have this expression for the conserved current coming from a rotation. That's the expression for the time component of that conserved current. And it's that gives us the density that we integrate over to get the conserved charge, which is then the generator of angular momentum. So this follows from, that's straight up Noether's theorem and substituting in. And then comes the bit where we write down the generator of angular momentum by the inverse Noether theorem. Thus, when you integrate J naught, this density here, over all space, you get the generator of Z rotations. That's the inverse Noether theorem. So this is the arguably much more interesting part of the Noether theorem is the inverse version, which no one ever has in any textbook. That promises us that when we integrate this density, we'll get the generator of the original transformation. Thus, I just did it for rotations around the z-axis, but the rotations around the y and the x-axis are exactly the same calculation, but with just some minuses and pluses and x's and y's. Oops, it's not quantum yet. Thus we get this expression here for the generator of the rotation of the bulk Dirac field around the kth axis. It's that guy that we're going to put the hats on and check that it is the generator of rotations coming from the Lorentz group in the quantum case. Yep. X. Yeah. This is X. Sorry, yeah, this is difficult notation. Actually, you're right. This is X, as in the position variable, and this is the cross product. So I could put a wedge here. I think you're mostly familiar with a wedge anyway. So wedge just means cross. And for anyone watching, that's probably not standard notation for you, but wedge is also just, in this course, a cross product, vector cross product. Now there's two, the thing to observe about this particular generator, as we've written it here, is that there's two contributing components to it. Now for the Klein-Gordon field, when we wrote out the generator of rotations, we only had this bit. There's an additional contribution coming here, and that's the contribution due to spin. So what tells us that our particles are spin 1/2 particles is they have this intrinsic angular momentum here, and of course that's just the contribution from orbital angular momentum right there. And the quantum generator, there's two ways we could have gotten the quantum generator. Way one is to believe my definition of the unitary representation of the Lorentz group that I wrote down, and then differentiate it. Or the second is to put hats on this. So there's two ways now, because I just wrote down this representation. It turns out way one is a bit uglier, so this is actually a more economical way to do it. So the quantum version isn't that much difficult to do. Just put hats on, and there it is. Now, there's one thing, the reason we did it this way is if you want to write this in terms of A's and B's, it's not very easy. If you substitute in our expression for the field operator in terms of A's and B's, then it's a kind of miserably difficult calculation. And that will somewhat hinder us in checking the angular momentum of our fundamental particles. So this is a somewhat lengthy calculation, so I'm actually going to stop here and start with that in the next lecture. So the objective for the next lecture is to check the angular momentum. So this is a generator of rotations. The question is, what's the angular momentum of one of our plane wave solutions? And the answer is it's going to be easy, because it'll have a spin contribution and an orbital contribution, but the calculation will be awkward because we have A's and B's in terms of momenta, which define the single particle states, and we have the generator, which is far, far better defined in terms of position here. And so it's going to be, we're going to need a trick or two to get that calculation to work out. So we'll do that in the next lecture, I think. Yes, we will. And we'll also solve the quantum Dirac field theory in the next lecture as well. So, but for now, I thank you for your attention.
Cool.